So, I'd like you all to be, what you say, more interactive. You can unmute and you can answer. If you're not able to unmute and everything, you can send a message. I'll respond to that. Okay, but I want you all to be interactive. It should be a two-way communication. This is not like the NPTEL recording where only sir is teaching you and you're just listening. It is not like passive. This I want you all to be active. I want you all to interact, to talk, to ask your doubts and queries. Okay. So the objective of these sessions is that you all are going through those lectures. There'll be some things which are confusing for you. You have to solve assignments, everything, and you have to submit that. So for those things, whatever doubts you have, you can ask. So what we do, like I am actually a PhD scholar in IIT Kharagpur. So this is like part of my PMRF teaching assistant duty. We conduct these NPTEL sessions. Okay, so in that case, what we usually do is we solve some previous year assignment questions. We'll teach some theory. We will solve some previous year assignment questions, and that will give you what you say your the idea of how you can tackle the week's assignments. All right. So these sessions I'll be keeping on Tuesday. It will be held on Tuesday from 6 to 8 p.m. and it will be on Zoom. So this is the link for Zoom. So there is one constraint which is there because I'm using Zoom is I don't have the what you call that, the pro version or the paid version. I have the free version. So the limitation is I can have only 40-minute sessions. So what I do is I have a 40-minute session. It gets completed. It gets automatically turned off. Then I again restart the same meeting. So you don't have to be worried of another second link, third link. No, there's only one link. You just have to join with that link and you will continue. Okay. All right. So now we will start. Okay. Week 1 digital electronic circuits. Okay. So, okay, let's be interactive. I want to listen to your voices, everything. I don't want to be talking to a blank screen. So let us start with a simple question, a very, very simple question. Okay. This is A, this is B, this is Y. So what is the symbol? Can anyone tell me?
And gate.
Yes. So very good. So this is an AND gate. Good. So this is a digital circuit, logic gate. Very simple one. So the truth table of this also many of you will know, but let me just write. So what do we write is we write 0, 0, 0, 1, 1, 0, 1, 1. So this is called a truth table. So I want you to tell me what will be the Y. What will be the output Y for each case? Come on, be interactive. Very simple question, very easy question.
So first one is
It is 0, 1.
0,
1,
0,
1, 1.
0, 1.
So, okay. So 0, 0, 0, 1. All right?
Right.
Yes. Okay, okay, very good. People are also answering good. Okay, so 0, 0, 0, 0, 1. So this is a simple AND gate. Similarly, we have OR gate and various other functions. The AND gate, we represent it as A dot B. Okay, A and B. Now, you also know what is a NOT gate, right? This is the symbol of a NOT gate. NOT gate. That is the input X and Y will be equal to X bar. So I have actually not taught to so many students at a time. Usually in Zoom, it will be limited to around 10. So this is a bit difficult for me actually. All right. So now you have various things. So can anyone tell me what's the full form of CMOS?
Complementary metal oxide semiconductor.
Okay. Complementary. Okay, my handwriting is quite bad, so I just hope you guys will bear with me. All right. So now there's a NOT gate, one simple NOT gate. Okay, we have also what is in it? TTL. TTL is there, transistor logic is there, there's RTL is there, there is DTL is there. Okay, various things are there. So for these, what I have done is I have also done some certain LTSpice simulations, which I will show you guys. Okay, some simple basic LTSpice simulations. So just when you see that circuit simulate, when you see the output, everything, it gives you more understanding. You can visualize things, all that. So certain LTSpice simulations also I have performed, which I will also be demonstrating over here. Okay, I'll be sharing my screen and demonstrating. So we'll start with a very simple thing is like digital means you either have 0 or 1. It is either low or high. Low or high. So this is a very simple basic question. Okay, this is a V output. This is some resistor R, RC, RB. This is your ground. And this is your V input. Okay. What does this circuit do? What is the objective and what function does this circuit do? Can anyone tell?
NOT gate.
Okay, very good. So this is a NOT gate, right? This is a NOT gate. So why do you say it is a NOT gate?
If you don't give any input, the output will be high. If you give high input, output will be 0.
Okay, okay, all right. So let's go with some numbers. Numbers are very good. So let us say VCC is 5 volt. So what does this VCC, when you see the symbol VCC and you see the symbol ground, what I want you to remember is that this VCC is connected to some plus minus 5 volt supply, and that is connecting over here. Okay. So there is actually a plus or minus 5 volt supply, which is actually this VCC. Okay. It is connected like this. So just, this looks cumbersome, TDS, everything. So we don't include that. We just assume that you all will mentally understand that there is some VCC, which is this 5 volt or 3.3 volt or 1 volt, anything. Okay. Then this is your output. Your output is measured with respect to your ground. Similarly, at your V input, you will have some test signal. Some certain test signal will be here. That also is connected to your ground. Okay. That also will be connected to your ground. So now, in this circuit, your RB is there to limit your current. It will limit the current which is going in. This is your IB and this is your IC. Okay. So when your V input is high, when your input voltage is high, that is, it is like, let us say 5 volt or 3.3 volt or some number, some voltage, what will happen is it will be more than this VBE. What is the VBE which we normally assume? Can you tell me?
0.7 if it is saturation.
Else?
Else less than 0.7.
Okay. So you have some VBE of 0.7 volts. So when your V input is greater than 0.7, etc., you will see this transistor will turn on. Okay, and there is the transistor can operate in various regions. That is, like active region. It can operate in cutoff, and it can operate in saturation. So when do you say that your transistor operates in active region? I asked a lot of questions, but hope you all will bear with
When
me.
VB
Hmm?
equal to 0.7,
Hmm.
it is called an active region.
Okay, let us see in a different way.
When it is between 0.6 and 0.7,
Hmm.
then it is active region.
Okay. Let me just draw better way. So this is your N, P, and N. Okay. So let us say this is your collector, this is your base, this is your emitter. Okay. So mm, so this is one of your junction. Okay, let us say this is your junction 1, this is your junction 2. Okay, that is you have a PN junction and you have another PN junction. So let us see what is the case. You have junction J1, junction J2. So the junction can either be forward biased or reverse biased. Forward biased means what? The voltage across that junction is greater than 0. Reverse bias means the voltage across the junction is less than 0. Okay. So now for junction J1, and how do we consider polarity is from the voltage from the P terminal to the N terminal. That is the polarity. If the voltage at the positive at the P terminal is more than the voltage at the N terminal, then we consider that the voltage is positive. Okay. So now when the transistor is in active region, what happens is this junction J1, that is between the base and the emitter, that is forward biased. And the junction between your base and your collector, that is reverse biased. Okay, that is reverse bias. When you go for cutoff, what happens is all the junctions are reverse biased. So this is reverse biased. This is also reverse biased. When you go for saturation, it means what? All the junctions are forward biased. All the junctions are forward biased. Any queries? Okay, this notes also I will be making a PDF of this and I will be sharing it on a link. And in that link, you can, access, you can check them. So that also will be shared with the NPTEL team. So there will be a, what you call that, a Google Sheet where you'll have the link to the drive link. So there'll be a drive link where all these lecture material, whatever I'm writing, will be uploaded over there. So you can refer to it. Furthermore, this session is since it is being recorded, afterwards I'll be editing, compiling all that, and this video also will be uploaded on YouTube. Okay, so you can access it there also. Okay, but in spite of all these provisions, I'll still recommend that you could also have a notebook with you and take some notes. Okay. Yeah, so Raj Aryan has told correct that forward bias, reverse bias is active region. Okay. So when you come in terms of digital, you want your circuit to operate either in cutoff or in saturation. You don't want it to work as an active state. You want to make that region where it will work in the active state as small as possible. Okay. Okay. So let me show you certain simulations. Okay, let me just pull it up. Just hold on. Mm. Are you able to see the screen?
Yes.
Okay. So actually, I haven't made the one for.
Yes, sir.
Yeah, I haven't made one for the circuit I drew. I'll just make a new one right now. So you need a you need a NPN transistor. So there's an NPN transistor is there. You can pick. This is a transistor model which is used a lot. So this is there. Connect ground here. Connect input here. Okay. Then so this is like a DC voltage source, which I'll give the value 5 volt, which I showed over here. Again, ground I'm connecting. This. Similarly, I need a resistor over here. Like this. So I guess many of you would have used LTSpice, but so you would know how to use it. So this, I'll give it a value of 1 kilo ohm. Another resistor, value of 10K. It's connected here. This another voltage source. This is my signal source. Okay. Connect here. Right. So this, I don't want it to be a fixed voltage source. Okay, let me give it a fixed voltage source for you for now. For start. Starters. 5. Okay. Admit. So now, let's save it. Okay, so this is a NOT gate. So let me do a simulation. Transient 1 milli. What's this? Screen like this. Okay. So this is the input signal. This is my output signal. Is this visible on the screen?
Yes.
Yeah. Okay. So this is a very rough, crude way. So let me draw it in a better way. So I'll walk through the steps. So what I've done, I've placed a 5 volt voltage source. That is like my VCC. Then I placed a transistor. I've selected a model 2N222 I've used. Then I've given some 1 kilo ohm resistor for my RC, 10 kilo ohm resistor for my RB. Now this also I've given a fixed voltage source. Okay, I can also give what is known as names, net. So if I give a name net, so let me give a name V in. Okay, this is my V in. So here I place my V in. That means this node, it will be labeled as a V in. Similarly, for my output, I'll give it a name V out. Okay, so I'll give it a net out, V out. Okay, this is my V out. This is the point of my V out in my circuit. Now, I don't want it to give a constant voltage. Like I want to test my digital logic circuit. My digital logic circuit goes high, low, 1, 0, 1, 0, etc. So what I will do is, this is my DC voltage source, right? I will right click it. This gives only a fixed value, but I want to have something which changes with time. So I will go to what is known as advanced. Okay, I go to advanced. There are various options are there. I go for the pulse option. Pulse option. Pulse option is, it either goes high, initial V on. Okay, I will show you. So my initial voltage, let me give it to be 0. V on voltage, I'll give it to be 5. Delay rise, we can ignore. Okay. On time, let me give it to be 2 microsecond. Let us do 0.5 microsecond. Period is 1 microsecond. Okay. I'll give it. So this is a pulse signal. My transient time, I will make it around 10 microsecond. Okay. and I'll simulate. Okay. Okay. So it's my name, right? Please, okay. Yeah. So the red one is my VN. It goes high, low, high, low. And this green one is my output. So when my VN is high, it is going low. When my VN is low, Vout is going high. But you will see that it is not going, it's not a rectangular curve. It is not a rectangular curve because there are certain limitations. There are certain capacitors are there, which you will also get to know about those things also soon. You will be learning about them. But because it has a speed, there's a limit in how it will go high and it will go low. There is a speed limit is there. That's why it doesn't go fast on and go fast off. So sir would have taught you something known as, if you would have seen the videos, which I trust most of you should do, there's something known as your propagation delay. That is the delay when it goes from, let us say, let me zoom in and show. Okay, and it's very silent. The class is very silent. I want you guys to talk. I want you guys to ask doubts. Okay. So the time it goes from 10% to 90%. That is your delay. That is known as your propagation delay. Okay. Any queries still here? Any doubts? It's the time. Okay.
This output we are taking from within the circuit, or normally it is emerging out from this point, huh?
Yes, it will be a point. Then this point will get connected to another logic circuit. So other logic circuits will get connected to. Okay.
Okay.
So this will go to another, like sir has taught the concept of fan out, etc. So this Vout will be act as an input for another logic gate. Okay, this Vout will act as an input for another logic gate and stuff. Okay, so this is just one small demonstration to show certain simulations which you could also do in your free time. So I think to save time, everything, let us start solving questions. Finally, you guys have to solve questions in the assignments, and you'll also have to solve questions in your exam. So we'll start with that. And I think while teaching the questions, some theory, the relevant theory also, I can explain that at the time. So because we need to finish those set of questions. So this is the set of questions. So I'd like you guys to tell me true, false, and all. So you have a CMOS logic. CMOS logic is complementary metal oxide semiconductor. You have NMOS and PMOS both. Both are same number of transistors are there. So what of these statements are true? Which one of these statements are false? You let me know. We'll note down and then I'll explain. We'll explain. That way is better. Assignment and theory we can explain simultaneously.
First one is correct.
Okay. CMOS has very high input resistance, hence draws low current. Okay, correct, true.
Second one is false.
Okay, you're saying it is false. What about third one?
Third one is also is correct.
Okay, third one is correct. So CMOS is faster than TTL.
Fourth one is also correct.
False.
Okay. Okay, and CMOS exhibits low power consumption. Okay, let me explain one point at a time. One point at a time. Let us go for, let us say this is question 1. Okay, question 1. So here basically this question is comparing between CMOS versus TTL. Okay. Now CMOS is currently the one which is in favor, which people are using a lot. TTL is like kind of old. It was what was traditionally used. It is, and in few circuits probably it is used, but mostly people are going for CMOS. Okay, the advantage with CMOS is it draws low current, as you have told. It draws low current because it's kind of like, it's a uh, MOSFET. MOSFET gate is like has acts like an insulator, so it draws very low input current. Okay, draws very low input current. Let me draw a circuit. So this is like your NMOS, and this is like your NPN transistor. So here, what is that? This is your collector. This is your base. This is your emitter, right? This is your drain. This is your gate. This is your source. So now the gate, and here this is like an insulator. So it draws very low current, whereas your base draws some finite amount of current. Okay. So that is one issue with your transistor TTL logic. So it draws low current. Also, it has very high input impedance. Impedance is sort of like another way. Impedance consists of resistance, inductance, capacitor, etc. But you can say that impedance is similar to resistance. So it has very high input impedance, so it will draw less current. So what do we mean when it draws less current is less current from the supply. I talked about this VCC, right? This VCC is what will draw current. From VCC, that is your battery or your source, there'll be some current drawn. That current drawn is less for CMOS as compared to TTL. So because that current drawn is less, the power loss is less. So it draws less current, your power loss also is less. So that is good. And CMOS is very good for packing. Like it is for fabrication. That is, when you are manufacturing, etc. CMOS technology is very good. So its packing density is high. Okay, its packing density is high. So there are so many good advantages of CMOS I'm telling. But there is something which is left. CMOS, they depends on the technology, everything and all. But CMOS usually is slower than TTL. CMOS is usually little slower than TTL. That is what is shown in the lecture material. So CMOS is slower than TTL. CMOS draws less power, less current, but it is generally slower. It is packing density is good. So that's why in mass manufacturing, now you see there are many op-amps, driver circuits, logic circuits, many of these things, they are made from the CMOS semiconductor. And the advantage is they can, pack 1,000, 10,000 million transistors in a very small area of space. Okay. So that's why CMOS has picked up very much. Okay. CMOS has picked up a whole lot. We are just touching very, very basic small part of CMOS, but there are more advanced courses as well, which you can also study. But CMOS is very, very good and used a lot for manufacturing, electronic manufacturing, and CMOS is like the semiconductor and stuff. Okay, so let us go back to the question. CMOS has very high input resistance and hence draws very low current. This is true. CMOS has high fan out as compared to TTL. No, that is false. The issue with CMOS is it doesn't have that high fan out. TTL has a little more fan out than CMOS. Then CMOS is generally faster than TTL. That also is false. Okay. Then CMOS has low packing density. No, this is also false because CMOS is used for manufacturing, and the reason why CMOS has got an advantage over TTL is like you can put lots of transistors within a small area. Okay, so that's why CMOS is used, and CMOS exhibits low power consumption. So the thing which are true is 1 and 5. And who's ADIR? Please don't write on my screen. Please don't write. Okay. So any questions in this? Any question? Any thing you want to
सर ऑप्शन
clarify?
2 भी इसका ट्रू होगा
क्या क्या?
सर ऑप्शन 2 भी ट्रू होगा इसका
ऑप्शन 2 भी ट्रू होगा क्या? अच्छा, एक्चुअली एग्जैक्टली हम लोग ठीक से बोल नहीं सकते क्योंकि इस को क्या बोलते हैं फैन आउट. तो फैन आउट means the number of circuits that can be connected at the output of a gate, at the output of a digital circuit. Okay. So for CMOS, as sir has also mentioned, it has more propagation delay. So because it has more propagation delay, this will limit the fan out. This limits the fan out. Okay. Whereas in the case of TTL, you have more current drawn, and that limits the fan out. Okay. So we cannot just directly compare CMOS and TTL, but as also someone was mentioning, see, this is based on the option answers which they have given. They have told that 3 and 4 is false. So 1, 2, and 5 are true. That is the correct answer. The correct answer is that 3 and 4 are false, and 1, 2, and 5 are true. Okay, let me just write it down so that you can refer later. So we have true are 1, 2, and 5. False are 3 and 4. So are there queries or can I proceed? If anyone has doubts.
Sir, please proceed.
Okay, thank you. Okay, so next is this circuit. So which logic gate does it look like? So this is the actual NAND gate circuit which sir has shown, sir has taught. Only sir has used 2 input NAND gate, but here they used 4 input NAND gate. So probably that is why it is confusing for you guys. Okay. So are you guys able to see my screen and the simulation LTSpice which I've opened up?
Yes, sir.
Okay, right. So this is the NAND gate TTL logic circuit which sir has shown in this lectures. So I made a simulation model of it, and I'd like to explain it to you guys step by step about how it works. Okay. So as you will see in this circuit, you will see over here. What do you see you have one, let me zoom in. So you have one transistor which has a base, it has two emitters, and it has one collector. Since making such a transistor would be difficult, all that I don't know the exact way, what I did was I used two transistors, and the bases of both transistors have connected and the collectors of both transistors have collected. So I have put it like this. Okay. So if you go here, the bases of both the transistors I have connected. Okay. And even the collectors also of both the transistors I have connected. That is why, so it is like multi-emitter transistor, but the base and collector are the same. So this is the input stage for your TTL logic. This is the input stage for your TTL logic. So that you have your VA and VB, they are your inputs. They are your digital inputs. VA, VB are my digital inputs. Okay. And this is the emitter is connected at the input. So the emitter is connected at the input. Similarly, here the emitter is connected at the input. Then what I have further done, there's a resistance RB, base also, because you know you have to limit the current. You just cannot have arbitrarily high current. As we have also discussed, like CMOS has very high resistance, but TTL doesn't have that much high resistance. These resistances also are connected and stuff. Then over here, this is your totem pole output, and this is another transistors over here. So sir has explained how it works. Like when this transistor is on, this Q4 transistor is on, then your Q3 transistor will turn on, and then what will happen? Your V output will be connected to ground. Else your V output will be high. Okay, so let us simulate and see. Let us, seeing is believing, so let us see the simulation results and let us see. So now, also there's a VCC supply which I was talking about. That is your 5 volt. Okay, VCC is your supply, 5 volt. All right. So now let me run the circuit. I'll run it. I'll show you. I have run it. What I want to see is, this is my input VA. This is my input VB. Okay, let me. Okay. I'll add a plot plane. All. So this is my input VA. This is my input VB. And this is my output V out. Okay. This is my output V out. So let me see for this level of circuits. Now what you see over here, VA is 1, VB is 0. So what should be my output be? What should the output be? Should it be high or low?
1. 1.
1.
Hi.
So it is high, correct?
High.
Yeah.
Yes.
When VA is high and my VB also is high, what is the V output?
So it should be 0.
Yeah, 0. Close to 0. That is low. It should be low. Next, my VA is low, my VB is high. What should be the output? Since it's a NAND gate, one is low, another is high. What should be the output?
It is 1. High.
High. Correct. It is high. Similarly,
Yes.
when both are 0, what should the output be?
It should be 1. High.
High. So it is high. Okay. So let me walk through what I've done. What I've done is I have generated some set of test signals. I've generated a VA, I've generated a VB. I have generated the test signals in such a way that you can get your 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, all. So all cases are covered in this. So you have a truth table. There's 2 inputs. So 4 cases are 4 outputs, 4 outcomes, 4 input combinations can be there. And the truth table's output I'm able to see over here. Okay. So that is distinctly visible, right? So I'd also like you to notice one thing is that my output, when it is high, it is not exactly 5 volt. When it is high, if you see the output is showing 4.9 volt, it is not exactly 5 volt. And when your output is low, if you will observe what is that voltage, should add a cursor. per server. When it is low, the output is in like in millivolt. Okay, it's in millivolt. It's not exactly 0, but it is quite low. Think probably I'm going a bit fast. If you feel I'm going a bit fast, you can even slow me down. But you let me know. You let me know how you're finding the pace. Whether you have doubts, you ask me. All right. So this is what we have done. What I've done is I've given a set of inputs which will mimic what inputs you will give for a actual logic circuit, and then you see the output. Now, when you see the output, let us see the output over here. You can see that the output is not immediately going low, right? It is not immediately going low. It has some time. It is taking some finite time. That finite time is all your what is the concept of propagation delay. Okay, that is your concept of propagation delay. Similarly, when it goes from low to high, okay, low to high, there's some amount of time it is taking. So that again is your propagation delay. This is your propagation delay from low to high. Okay, you can measure this using cursors, everything you can measure. But this that concept. So like I want you to feel it. That there is a delay. It's not like 1 means immediately it will go to 0, 1 0 immediately will go to 1. It's not like that. There is a finite time. If the time is as small as possible, it is very good. But you should keep in mind that there will, in a practical circuit, there will be certain delay. Okay, so there's certain delay, right? So now, if my input, as they have asked in the question, let us go back to our question. What does the question say is, if all the inputs A, B, C, and D are at logic low, what should be the output? So all the inputs are 0, 0, 0, 0, 0. So this is like a NAND gate which has 4 inputs. So what should be the output?
Output is high.
Output is,
High.
okay. Output is high. So similarly, like I could also modify this. I'll leave that for you guys to do. Okay. You guys are, this whole circuit is visible to you guys. You can also make these circuits on your own. It'll be very interesting to make these circuits on your own and to check. So then you are actually, getting that feel and everything. It will be good for your projects and other things. I actually currently don't know, like, you guys are in which year, whether you're in bachelor's, whether you're in master's, whether you're PhD, or whether you're teachers, professors, I don't know. But you can let me know slowly. As the course goes, you can introduce yourselves and you can let me know what you're looking also from what you want from this course, etc. And you can please provide lots of feedback. It's very important. Yeah. So second question also, we have gone through it. There's just some additional transistor, additional inputs, but it's the same NAND gate logic. So if all the inputs are low, okay, then what your output will be 1. It is high. Okay. Next, we'll go for this one. Okay. This circuit. Question number 3. Okay. Now, in this question, okay, let us see this question. Again, it's like similar. It's about TTL and DTL. So in TTL circuits, the rise time should be low, but fall time can be high. In CMOS circuits, the fall time should be low, but the rise time can be high. Both rise time and fall time of a DTL circuit should be as high as possible. The figure of merit of a TTL circuit should be as low as possible. The average power dissipation of any logic family circuit should be as low as possible. Okay. So, any answers? You give me your answers. Be interactive. Ask, tell answers. Okay, there are no points. There's no daily evaluation or other schemes like that. Where I can cut your points. I have a roll list. Know who's answering, not answering. There's no concept here. You answer what you think. Okay. What should be the answer?
So fifth is true, huh?
Yes,
That
that's
is
very
there.
correct. Okay.
That is
Next.
true. That every power dissipation.
Okay, very good. Next.
First is true, sir.
Okay, rise time should be low, but fall time can be high. Acha. Why? Why do you say? See, your answers cannot be digital. Okay, true, false. That's not the way. Answer should be true with reason, false with reason. You can tell your reason. Your reason can be wrong, but I prefer reason also with your true or false statements.
TTL uses BJT, that's why.
Mm-hmm. Okay. All right. All right. Okay. Next. What about others? What about others? Like we have many students. Okay, I'm not taught to so many students at a time, so it's difficult for me as well. But I still trust you all can. All of you can answer. Can participate. So it talks of TTL circuit, it talks of CMOS circuit, it talks of DTL circuit, various types of circuits it talks about. But as I was showing in the previous simulation, we want the rise time, fall time, all to be as small as possible because it is a digital circuit. Since it is a digital circuit, you don't want your output to be at an indeterminate value, indeterminate number. Okay, so let me just go back to the simulation once more and clarify what I mean. If you see this case, okay, if you zoom into this portion, here the output initially was low, now it is going high. Now, when you will notice this, how do you know it is high? How do you know it is low? There is some place where the value is not exactly high, it is not exactly low. And that is your rise time, fall time, delay, propagation delay, etc. So what you want is you want to design your circuit, you want to size your transistors, you want to select the value of resistors, all that, such that that time is as small as possible. You want that time to be as small as possible. So whether it is a CMOS circuit, whether it is a TTL circuit, whether it is a DTL circuit, you want your rise time and your fall time to be as small as possible. Okay. So we will revisit the question. You want your rise time and your fall time to be as small as possible. That is what you want. There's a difference whether it is possible, it can be done, it cannot be done is a different thing. But what you want is it should be as small as possible. So if the statement is that you want your rise time and fall time to be as small as possible, if that is what is the desired truth, then all these first top three statements are false. Because you cannot have it to be high. You cannot say that I can have the time to be high. It can take more time to go from high to low, low to high. No, that is not what you want. A good design will not do that. A good design wants that time to be as small as possible. You will force the designer to make that time as small as possible, which he can do. Okay, so that is a case. Next is something known as figure of merit. Figure of merit is like how good it is, how good a circuit has been designed, and etc. So, in the case of, let me write it. So, you have question 3. You have FOM. Okay. If you add O, then it is FOMO, fear of missing out. But okay, don't get confused. So, this is just figure of, I think of only one of, figure of merit. Okay. Figure of merit is actually your power dissipation into your propagation delay. So we already were discussing that the propagation delay, you want it to be as small as possible. You want your circuit to go high, low as fast as possible. So your propagation delay should be small. your PD stands for power dissipated. That is how much power your circuit is consuming. So I think we saw it in the first question itself. Your power dissipation also should be small. So what you want your figure of merit to be low. You want your figure of merit to be low. As small, if your figure of merit is low, that means your design, your circuit is good. If your figure of merit is high, then it is a bit of a problem. Okay. I hope there's no doubts in this.
Yes.
Okay.
No, sir.
Yes. And similarly, the average power dissipation should be as low as possible. All right. So now, okay, there's this circuit. What does this circuit do? And which logic family it is a part of?
DTL and the TTL.
Yes, correct. It is a DTL. Okay. Okay, it's a DTL circuit and it is again a NAND gate. Okay, it's a NAND gate. So sir has used the NAND gate circuit a lot for demonstrating the concepts of various transistor families and all. And there is a reason also, because NAND gate is one of the universal gates. So you all would be knowing that NAND gate and NOR gate, they are the universal gates. So if you want to make any logic circuit, any of AND gate, OR gate, all that, you can make it by a combination of NAND gate and NOR gate. Because like the NAND gate and NOR gate are the fundamental building blocks. So you use those building blocks and then you can make another logic circuits. Okay. So that being said, so this is a DTL logic, okay, diode and a transistor logic. There are certain resistors also are there, but still they give it the term DTL. Now, if you will see this circuit, you have this transistor is there. So if this transistor is on, what will the output be? If this transistor is on and the output is at Y, what will the output Y be? Will it be high or will it be low?
It is low.
Yes. So if this transistor is on, that means your output will be low. But if this transistor is off, what will your output be?
Low.
Why?
High, sir, high.
Because
Yes.
because
Okay.
because base is connected to emitter via the R3 resistor.
Okay. So
So this will drop out the voltage across VB.
okay. But at the output Y. Tell.
Then the output will be getting lower, right?
No, like basically this is a logic circuit, and basically depending on what voltage comes over here, this voltage is high, some high value, more than the threshold voltage. Then what will happen? Current will start flowing, and this transistor will turn on. When the transistor turns on, the voltage across the collector and the emitter of this transistor will be driven to saturation. So VC saturation, you assume it to be like 0.2 volt something. So your output Y will be low. Okay, output Y will be low. When VBE is not high, okay, when VBE is low only, that when the input over here is low, that means this current is not flowing. So then the transistor will be in cutoff region. If it is in cutoff region, what will happen? No current is flowing. Since no current is flowing, there will be no current flowing even through this R2. And if no current is flowing to this R2, then what will happen? This Y will have the same voltage as VCC. So that's why Y will be high.
The pull-up voltage.
Like pull up sort of. Okay. So this is actually a NAND gate. Let me show you the simulation of this also. So, NAND gate ETL. Yeah. Okay. So this is the same circuit. You have these diodes here, you have these diodes here. Similarly, like how I showed, the test input, that 1, 0, all 1, 0, 1, all 0. You can see, if you will see, let me zoom in and show you guys. Again, this follows the truth table of NAND gate. That is, both are on, both are high, then the output is low. Else, if anything is low, the output is high. Okay, this is the NAND gate truth table. So now the question is saying, what is the purpose of this resistor R3? What is the purpose of the resistor R3? Anyone has
Sir,
any
to control the transistor.
control the transistor? But in the previous circuits which I showed, NAND gate TTL, all that, we didn't have this resistor R3. Let me open that also.
Sir, I think if we don't connect it, so always the output lower due to ground.
No. Okay, let us see.
The help of the transistor R3
Could you repeat
is
again?
to make the transistor to discharge through it when it's
Correct,
turned off.
correct. That's correct. That's the answer. That's the answer I'm looking for. Okay. Very good. So, okay. Uh, mm, what was your circuit? You have this resistor R. You have this transistor here. This is your V output. This is your input. This is your resistor R3, right? This connected to ground. And these are all your diodes here. And the extra circuit over here. Okay. So, what happens? There are two cases, whether this voltage is high or low. High or low. So, when this voltage goes high, like this point P is the input to this case, when this voltage goes from low to high, what should the output voltage? Output voltage should go from high to low, right? High to low. And then when this goes low, this should go high. Okay, this is the way, which I can also show you in your simulation. So what actually is present is, there is this capacitor. These are known as these parasitic capacitors, all that are present for the transistor. So now, this is your voltage over here, the voltage over here. When you give high, okay, what circuit it looks like? This capacitor is there, it will get charged. It will get charged. Okay, this capacitor. And again, this same thing is there. This also is there. Okay, this also is there. Let us actually draw the let's draw the capacitor. Okay, it becomes charged. It becomes charged to your voltage, 5 volt or whatever voltage is there. Now, you want to discharge it. But when you have these diodes over here, current cannot flow in this direction. Your current wants to flow in this direction, but it is not possible. So, to allow some path for the current to flow, we connect this resistor R3. Okay. Such that the capacitor charge can be discharged. This is a bit advanced, but let me read out the options so it will give you more sense. what they're saying is R3 increases the output resistance in the transistor circuit. So R3 should be as high as possible. That is not the case, right? R3 is not at the output. R3 is at the input. Then R3 only performs proper biasing of transistor. R3 should be as low as possible. That also is not true because there's no concept of biasing. Either you turn on the transistor or you turn off the transistor. Biasing is more when you do design amplifiers and other stuff. Okay, this is not the case. Then R3 is used to reduce the propagation delay and proper biasing of transistor. R3 should be as low as possible. This could be the answer. Because why? If you want your R3 to be low, if your R3 is low, what happens? The capacitor which is formed over here, it can quickly discharge. It can quickly discharge, right? If your R3 value is high, then it will not quickly discharge. And another thing regarding this resistor R3, I was saying proper biasing. See, R3 only performs proper biasing is not the answer. R3 can perform biasing in the case that if there is no input voltage applied, there is no current flowing, then it will pull this voltage to 0. It will pull that voltage to 0. Okay. All right.
So it can also helps to proper biasing also.
Yes. Yeah.
Okay.
So let me. Actually, what has happened here? Laptop is slow. I'll do a test case. Okay, I'll change the value of R3. Say RB or parallel. Then so what is that known as spice director? Let me edit one. Okay. Okay. Read this. If you will see, there are different curves. If you will notice, there are different curves. Those curves are for different value of resistor. So this curve is when the resistor value is lower, and these curves are for different value resistors. And let me see, there was a way to add it actually. Yeah. Okay. So what I've done is I have changed this value of this resistor. I've given it a variable name where it can have various cases. It can be 100 ohm, 200 ohm, 300 ohm, 400 ohm, 500 ohm, different values. And I have simulated it. So what you will observe is that the time when the resistor is low, it changes very fast. When the resistor is more, it takes more time. The delay is more. The delay is from this point to this point. Okay, so as you increase the value of resistance, your time for which it takes for it to go from high to low, low to high will increase. Okay, so what people do is they run these different simulations for different test conditions, different value of resistors, and then they are able to identify which value of resistor will work well. Okay. Any queries? Okay, so let's go. I'm actually going quite slow. So okay. What is the value of the voltage of the collector terminal when both the inputs A and B are at high voltage plus 5 volt? You consider current amplification factor of a transistor to be equal to 100. Voltage drop across diode is 0.7 volt. VCC is 5 volt. R1, R2 values are given. R3 is this much. VC saturation is 0.2 volt. So they are saying both inputs A and B are high. So which logic gate this is?
NAND.
NAND gate. So if both inputs are high, what should be the output?
Should be low.
It should be low, correct. So if it is low, what should be the value? Why should it be minus 24 volt? Should it be 5 volt, 0.2 volt, or 0.7 volt? What value should it be?
0.2 volts.
0.2 volt. Why? Because since it is on, the transistor, lots of current is flowing to the transistor, and there will be a small voltage. That voltage is the saturation voltage of the transistor VC sat. That is why the voltage will be 0.2 volt. Okay. Any questions? Okay.
Sir, repeat, sir. Please, this how it is coming 0.2 because it is in the saturation.
Yes. It's in saturation. Because it's in saturation. So what happens is we know that the output should be the lower high, right? It should be the lower high, right? So if this transistor is off, if this transistor is cut off, then what happens is no current flowing here. Let me draw this because this is a very important concept which will be used in many places as well. So let me draw it once. So this is the circuit. This is your R, this is here, and this is your V output. This is your VCC, and this is your ground. Okay. Now, this is your transistor T. T has two conditions which we are evaluating. It is either on or off. Okay. So let us consider case when it is off. Okay, when it is off. Let us look at this case. When it is off means this current drawn, that is the, let us say, VCC R comes here. This is your V out. Collector, base, emitter, right? When it is off, if this is off, what does it mean? The current drawn is 0. This current drawn is 0. And since there's nothing connected here also it is 0. That means current drawn over here also is 0. That's why your V out will be equal to VCC. Okay. Since no current is being drawn, it is pulled up. It is pulled up to your VCC. Okay. Now the confusion is when it is on. The confusion is when it is on. So when it is on, how it looks like, you have your VCC here. You have some R here. You have like this here. This is your V out. So current is being drawn. Okay, there's some current being drawn here. Current is drawn here. Current is drawn here, and it is going to ground.
So V out 0.
No. V out will not be 0. There will be some voltage over here. There's some voltage known as VCE sat, saturation voltage. So when it is on, this VCE sat, which is equal to 0.2 volt. So that is why your V out will be 0.2 volt in that case. Your V out will not be 0. It will be 0.2 volt. Because you see, you should understand that when your transistor is on, means it is drawing, current is flowing through the transistor. And it is not like the transistor has zero resistance. Transistor also will have some finite resistance. And all these things, it is modeled as some voltage. Some voltage will appear. That is known as your VC saturation. Okay, that is your 0.2 volt.
Okay, sir.
Okay. So I think it should be here also, it should be visible if I'm not wrong. You see over here. If you see this voltage, sorry. This is when it is off. Okay, the voltage is little less than 0.1 volt. Okay, little less than 0.1 volt. So that depends on the transistor. 2 and 222 may have some different VC saturation, etc. But I want you to know that this voltage is not zero. It is some voltage. That is known as the VC sat of your transistor. Okay. Is this point clear?
Okay, sir.
I'll start with this question 7. Then we'll go for CMOS circuits and all. Okay. So now, this is another circuit. If you will notice, is my screen, you're able to see the screen, right? All good?
Yes.
Okay. So there's a driver circuit. If you will remember, like this is again a kind of like a NOT gate. This is a NOT gate, which is connected to another set of some other set of NOT gates. Okay, there are many NOT gates connected. There are various NOT gates connected. Now, we'll consider a simple example. You have your RC over here. You have your transistor over here. You have your RB over here. And this is your V input. Okay, V input. And then you have another RC. This is going to an RB. This is another set of transistor. So this is your V out. And this is your V out 2. Okay. And these all are connected to your plus VCC. This is connected to your ground. This also is connected to your ground. So if you will see the circuit, what actually it is made up of, this is one of your NOT gate 1. And this is another of your NOT gate 2. Okay, you have a NOT gate 1 and you have a NOT gate 2. So what is the problem over here? Your V input is high. The V input, suppose your V input is 1. V output will go low. And this V output 2 should be 1. Because not, again not. Now your V input is 0. Then your V output will become 1. And your V output 2 should become 0. Okay, but there is a problem which happens. What is the problem is, when your V in is 0, your V output should be 1. And what is that voltage over here? What is this V output voltage? Your V output voltage is equal to VCC minus your IC into RC. Okay. It is VCC minus IC into RC. In the previous case, what happened was, when we were showing the circuits, was like in the circuit which I showed over here, there was nothing drawing current. This current was 0. But since you have connected another logic gate, there is some current that could be drawn. And that is equal to the base current of the next transistor. Okay. So now there is some current being drawn. And because that current is drawn, this voltage over here will reduce. This is if you have connected one transistor in the output. If you connected multiple transistors, this voltage will go lower. It will fall. Okay. So that is why they have some voltage, what is known as your V input H. As long as this voltage V output is greater than V input H, it is fine. Or you can work with it. It can work. But as soon as let me write. If your V output is greater than V input H, it is all right. But if your V output becomes less than V input H, then it is a problem. Okay. So in our question, what they have given is V input H is, what is your V input H over here? V input H is 1.5 volt. Okay, it is equal to 1.5 volt. So V input H is equal to 1.5 volt. So if this V output is 1.5 volt, then it is fine. So let us find how much is the current drawn. Let us find the current drawn. So your IB is equal to V input H minus your VBE by your RB. So that is equal to 1.5 minus 0.7 by RB is 10 kilo ohm. So that is why it becomes 0.8 into 10 to the power minus 3 ampere. So your IB becomes equal to 8. 1.5 minus 0.7 is 0.8 divided by 10. So it becomes equal to 80 microampere. Okay, your IB is equal to 80 microampere. Now, if there is another logic gate, okay, which has another RB, and it further goes on, so more and more current will be drawn. So then your V output, which is actually equal to your VCC minus ICRC, this V output can go as low to VIH. And this is VCC. And this IC is what? Your number of gates which is connected into your beta current into RC. So that is why your N will be VCC minus VIH upon IB into RC. Okay. So in your case, VCC is 5, VIH is 1.5. 1.5, IB is 80 microampere, RC is 1 kilo ohm. So what is this value? Can anyone tell me? No one has the calculator with them.
I get 0.4375.
What value? What value?
Yeah, 0.4375. I don't know if it's correct.
Oh, no, no. So it is actually equal to 3.5 divided by 8 into 10 to the power minus 3. Someone should have a calculator. Let me use my phone calculator. There's 0.0 8. 3.5 divided by 0.08. 43.75. Did you get that?
Yes, it is 43.75.
Correct, correct. So it is 43.75, but you cannot like have
Yes, sir. Yes, sir.
0.5 of a logic gate connected. So you will take the lower number, that is 43. Okay? You will take the lower number, that is 43. Acha. Okay, good. So now let us, then they are saying you have to have a noise margin. Noise margin H. What is that noise margin H value given to be? Noise margin H is 0.8 volt. Okay. So you want this voltage over here, this V out voltage over here. It can be your VIH plus this 0.8. So it should be 1.5 plus 0.8. It's like, the safety factor, various things which you consider while designing circuits, all that. So you have this safety factor. So it'd be 1.5 plus 0.8. So that means your V output can drop as low as 2.3. If it drops more than that, it is not acceptable. So we will consider case when your voltage at V output is 0.8, that is your noise margin, plus your VIH, that is your 1.5. So the voltage at this V output node is 2.3 volt. Okay, when your voltage at this V output node is 2.3 volt, then how much current will be drawn by this circuit? That is equal to 2.3 minus your VBE divided by the resistance RB. So that is 2.3 minus 0.7 divided by 10 into 10 to the power 3. That amount of current. Similarly, current will be drawn by this transistor, this transistor, this transistor, this transistor. We assume all the transistors are identical. So they draw the same similar amount of current, right? So now, since that is our assumption, what we can do is noise margin H is 0.8 volt. So your V out will be equal to your VIH plus your noise margin H. So that is equal to your 1.5 plus 0.8, that is equal to 2.3 volt. So now, this is your voltage V output. This connected to this was your initial gate. This is your first stage of NOT gate. Okay, this is your first stage of your NOT gate. That output is going to your another lots of set. So there are another resistor over here, another resistor over here. Many resistors are there. They are followed by various gates, etc. So let us consider one gate. Okay, we are just considering for one gate. So this is your RB, this is your VBE, right? So let us we are calculating how much current IB is drawn. So your IB will be equal to your V output minus your VBE divided by your RB. Your V output, which we told it can reach the value 2.3 volts, so it is 2.3 minus 0.7 divided by RB, which is 10 kilo ohm. Okay. If you do the calculation, it comes out to be 160 microampere. Okay. Okay. So IB is 160 microampere. So now, yes. Okay. So many people are getting the answer, but let me just solve it for everyone else. So as I told you, V output is VCC minus IC into RC. So your V output we told 2.3, VCC is 5, IC is what? N into your IB into your RC. So your N in this case will be equal to 5 minus 2.3 is 3. No, it is 2.7. 2.7 divided by 160 into 10 to the power minus 6 into RC is 10 to the power 3, which if you do, it will come out to be 6.875. So we take it as 16. So you can have 43 transistors connected, or you could have 16 if you have the noise margin of 0.8. Okay. This is a hard sum, I'll admit it. But if you have any doubts, you can ask me. No questions? Okay. So I'll proceed then. So what I start with, something which I should have done at the start, is about CMOS circuits. CMOS circuits. Okay, CMOS circuits are very useful. We talked a lot about its advantages, disadvantages. I think we spent too much time there. So now let us say for CMOS circuits. So what is a CMOS circuit? It has your this is your PMOS, and this is your NMOS. Okay, VCC. This is how the circuit looks like. So let us see for simple inverter. Okay, this is for an inverter. So this is your V input. This is your V output. So if your V input is high, okay, your V input is, let us say it is high. It is 1, or let us say it is high. Then what will happen? Let us consider for NMOS, PMOS, V output. Okay, and this is your V input. Your V input is high. Will your NMOS be on or off?
NMOS will be on, PMOS will be off.
Correct. So what will be your output?
It is 0.
Low. The output is low. Similarly, when your V input is low, what will your NMOS be on, or will your PMOS be on?
PMOS will be on.
PMOS is on, NMOS is on or off?
Off.
What will be your output?
It is high.
It is high. Correct. Right? So this is your CMOS inverter. So this is very nice. So you must remember that for every PMOS, there will be an NMOS. Now let us draw for a NAND gate. NAND gate. NAND gate is like this. Okay. This is your V output. This is your VCC. A, B, A, and B. Admit. Okay. Now can you tell me, why is this a NAND gate? Why is this a NAND gate? How is it? So you have A, B. Let us say this is your T1, T2, T3, T4. Okay. Let me make space. A, T1, T2, T3, T4, and B also. So A is 0, B is 0, 0, 1, 1, 0, 1, 1. You tell me. What will happen? To simplify, let us just
AB00. AB00 means T3 and T4 will be on.
yes. Okay, and T1 and T2 will be off. So your V output will go to high. right? V output will go high. Now, if you see, the main thing which plays a role is this part. Only if both A and B, only if both are high, then only your V output will go low. If both are high, then only this will get connected, this will get connected, then only they will connect to ground. If any one of them is low, this closed path is not formed and your V output will always be high. Okay. V output in that case will always be high. So only if T1 and T2, only if both are on, and when both are on, what will happen? V output will be low. Else if in any case they are off, any one of them is off, it will automatically be connected high. It will automatically be connected to high. Okay. Then let us see a NOR gate. If any doubts, please ask me. Please ask me. Many of you are very
For NAR,
silent. Tell.
for NAR gate, the transistors will be shuffled. Like for NMOS, we will be replacing by PMOS. Is it so?
No. I'll draw. For a NOR gate, this is the circuit. You have, this one here. Here, VCC, V out, A, B, A, B. Then this is connected to ground. So here they are connected in series. Here they are connected in parallel. Okay. So now you tell me, if any one of A or B is high, if any one of them is high, your V output will get connected low. If either A is high, then this transistor is on and it gets connected low. If B is high, this transistor is on and it gets connected low. Right? So if you draw it A, B, B output, if anything is high, any one of them is high, it will go low. The output will go low. Only if both A and B are off. If A and B are off means what? This is on, the PMOS will be on, and then the output will get connected to high. Right?
Yes.
Okay. Yeah, please be interactive. So, yeah, this is a bit difficult if you have not been exposed to CMOS circuits. It will take time to understand. It will take time, but this is a very interesting thing. So, just be active. Please be active. Keep talking, keep asking doubts, right? So, what I want you to remember when you look at CMOS circuits, it is very intuitive, very much based on understanding is, if here it is connected in parallel, if the PMOS are connected in parallel, then the NMOS has to be connected in series. That is fixed. And if there's an A, should be another A. If there's an A connected to a PMOS, there should be an A connected to an NMOS. That is why it is CMOS, complementary. There is another complementary circuit of that. Okay, another complementary gate is that. So wherever there's a PMOS, there should be an NMOS. If the PMOS is connected in parallel, then the NMOS has to be connected in series. And vice versa. Okay, in NAND gate, as you saw, these are connected in parallel and these two are connected in series. If you consider for a NOR gate, these two are connected. The PMOS are connected in series and the NMOS are connected in parallel. Okay, so this is the way you represent it. Okay. All right, so let us start with one very interesting question which was there over here. Mhm. Okay, are you able to see this question? Are you able to see the circuit?
Sir.
Okay, so very interesting circuit. So this is A, this is point A. What will be the value over here? So this will be A bar, right? Because this is an inverter. This is an inverter. Similarly, this is another inverter. So this over here will be B bar. Okay, so from A I got A bar, from B I've got B bar. Very, very good. Now if you look at this, is this a NAND gate or a NOR gate? This part, this part, is this a NAND or NOR?
NAND.
Very good,
It's
very good.
NAND.
This is NAND, right? And the output of the NAND gate is what number? Okay, the output of the NAND gate is something. That output we can write it as X bar, right?
X
Because
bar.
again there's an inverter. Yeah. Similarly, this is Y, so this output also is Y bar, right? Okay. So this is X bar and Y bar. We got X bar, Y bar. Now we want to find what is X bar in terms of A and B, right? So X bar, what are the inputs to this NAND gate, to this NAND gate 1? What are the inputs? Can you tell me? There are two inputs to this NAND gate. So what are those two inputs?
A bar and B.
A bar
Exactly.
B.
So you have A bar and B. And since it is a NAND, there's another complementary sign, right?
Yeah.
Similarly, Y bar is what? What are the inputs to Y bar?
A B bar.
So it is A, B bar, and NAND. So again, this is the case. Then what do we do? Since bar is there, so what we can write? We can write X is equal to A bar B and Y is equal to A and B bar. Can I do this? Am I, doing blunders, or is this allowed?
It is according to De Morgan's law, the A bar or B bar should come.
No, but this also has a X bar. This also has a bar, right? So both bar are
Okay,
there,
okay.
so they get cancelled out.
Yeah,
Right?
yeah.
Even over here it gets cancelled out. So I got X and Y. So this is like
Yeah.
so this is like a trick. Like you can, as you will do more and more circuits, you will understand. Instead of giving it another variable P1, P2, and then writing in terms of X and Y, directly I wrote it in terms of X. So I got X bar, I got Y bar. Since it's a NAND gate, very good way, I could got X and Y. And if you will further, when you, as you grow more advanced and all, you'll realize that this overall thing, this is your AND gate. Okay. This is overall your AND gate. So we just broke it into steps, but it is what it is. All right. you'll learn to appreciate it better as you proceed. So what we got X and we got Y. Now they are saying we want another logic gate. Another logic gate is required. Okay. You will take X and Y as an input and it will give rise to Z. Okay, it will give rise to Z. Now, and they want us to find out what should be the logic gate. So they are saying we have A, B, and we have X. Let us see, sorry. We have A bar, B, B bar, A. Okay, A bar dot B is, this is X, this is Y, and they want another Z. And the question says is, they want Z such that A XOR B. Okay, this should be A XOR B. Okay. So XOR means what?
A bar B plus
That means the output is
A
0,
B.
1, 1, 0. Right?
Yeah. Yeah.
So can you tell me what is A bar dot B? A bar and B? What is X?
XNOR.
0. 0.
Here it is 0.
0, huh?
Here it is
0.
it will be 1, right? Because it will be A bar is 1
What is
and
1?
1. Yes. Then over here,
Yeah.
1, 0 is 0, 0. Right? Because A bar is there.
Yeah.
So wherever A bar becomes 0, it will all go. So this is the case. Similarly, B bar dot A. So B bar dot A is 0, 0, so 0. Then here it will be 0. Then here is the case where it will be 1. Here the case where it will be again be 0. Now they want you to generate this number. Okay. So from X and Y, you need to generate this. So this is simple OR gate. You can use a OR gate. You can use. So you connect X, you connect Y. Array, sorry. So my drawings are very pathetic, but I apologize for them. Okay. So if you use an OR gate after X and Y, you get this circuit. Any questions? Any doubts? No questions? I don't know. I don't know whether I should be very happy that I'm teaching so well, no one is having questions, or I should be very sad at teaching very bad. No one is understanding anything. Okay.
Good, sir. And we understand better.
Okay, good. Thank
We
you.
are following, sir.
Yeah. But please be more vocal, right? Okay. Next. So now we actually have less time, but let us see. Okay, this is an interesting circuit. Okay. So now this is A and B. Okay. This is an AND gate. So this is A, this is B. So this output over here is what? A and B. Right? Now, since this is A bar, this is B bar. So this is A bar and B bar. It's coming over here. Good? Till here, any doubts? Is it all clear?
No.
Yeah.
No, sir.
Okay, good. Now, this is NOR gate, right? This is NOR gate. So since it is a NOR gate, let us say this is your X, this is your Y. So this is actually a X plus Y bar. Okay, X plus Y bar. So we'll make it very simple. So we do A, B, which is your X, A bar and B bar, which is your Y. Then this, let us say this is Z, and this is your Z, which is your X plus Y bar, this is your Z. Okay, and the light bulb we'll see later. So A, B truth table, so you have 0, 0, 0, 1, 1, 0, 1, 1. Okay, A and B is simple, so you have 0, 0, 0, 1. A bar dot B bar, it is actually an OR gate. No, it is actually, this, if I'm not wrong, this is a NOR gate. This is a NOR gate. Okay, let us do. So what is A bar and B bar? What is the value? Tell me.
1.11.
1. Then?
Dot 0, 1.
Again 1. See, this is 1. Then you have a 0 here. A bar dot B bar also, this will also be 0. And this also should be 0. Is this right?
Yes, sir.
Okay. Okay. Now this is X plus Y. X or Y. And then you invert it. So what X or Y means 0 and 1 or becomes 1. Inverted, it becomes 0. Okay. Similarly, X or Y over here, 0, 0 means OR is 0.
0.
So
1, 1, 1.
OR is 1. So
1,
here 1.
1,
Here also is what? This I think is 0. Yeah,
0.
0. Okay. Now this is your supply plus 5 volt. This is your light bulb. When will your light bulb glow? When will your light bulb glow? When Z is 0 or when Z is 1? In which case will your light bulb glow?
In 1.
Okay. So this is actually very digital questions. It is either 1 or 0. Okay. So what about others?
Only when
One.
the output is 0,
Mhm.
then only the light bulb will be glowing.
Correct. Okay.
Why? Because the light bulb is being given as an LED.
Correct.
So if it is the cathode of that particular light bulb is going to be 0, then at the time of that only the bulb will be glowing.
Exactly. Very good. Very good. So you have your supply VCC. Okay. You have your resistor over here. Then you have a diode over here, which is your LED. And then you have this point Z. Okay. Z can have two options. It can be either on, like it can either be high or low, right? So let us see VCC. You have your resistor, you have your LED here, which glows. And then if this is low, connect to ground, means current will flow and your light bulb will glow. If this is VCC, this is R, this is again your LED. This again is connected to VCC because it is high, right? So current over here is 0. So your light bulb will be off. Okay. So we'll quickly just go through this. I think I'll next time set up for, it'll auto admit. Otherwise, I have to manually admit it is getting problematic. That I'll do for next meeting so that time can be saved in that. So if you look at this circuit, what do you think? Which operation it is performing? Okay, since we are in a shortage of time, let me tell you, so it's a NAND gate. Why it's a NAND gate? Because you see they are connected in series, right? So if both A and B both are on, then it will be pulled low. Else, if either A or any of either A or B is off, this path is not formed and it will automatically be pulled high. That is why this circuit will perform NAND gate operation. It will perform NAND gate operation. So I'm really going in a hurry because today it has got delayed. Your time also is important, but I'm just telling you certain stuff. Okay, for this question, role of level shifter in detail is to increase VIL. Then in this circuit, what happens is you just TTL. So this is actually in inverse active mode. TTL, this transistor T1 input transistor, it works in inverse active mode. Right. Then question 14, power dissipation is 50 milliwatt. Propagation delay is 25 nanosecond. What will be its figure of merit? So as I mentioned, figure of merit is the power dissipation into your delay, into your propagation delay. That is 50 milliwatt into your 25 nanosecond. So that if you compute, it will be come out, I think, to be 1.25 nanojoule. Okay, 1.25 nanojoule. So B milli means 10 to power minus 3. Nano is 10 to power minus 9. So these numbers you should know. You have to do multiple times. You have to solve sums, know the numbers, get it right. Right? Then your errors, blunders will be less. Okay. Okay, this is quite a difficult circuit. We can also look into it if you guys have time. In this is one question. Okay, this is a very interesting question. So let us check this. I'll do fast because already it has exceeded a lot of time. VOL is 0.9, VOH is 4.5. So this is your VOL is 0.9 volt. VOH is 4.5 volt. Okay. So so this is when it is high, when it is low. Okay. Similarly, so they told you have input 1. In the case of input 1, what is your VIL is 1.2 volt, VIH is 3.2 volt. Okay. So this VIL is 1.2 volt. Your VIH is 3.2 volt. So this is your noise margin of high. This is your noise margin of low. Okay, you can compute. Noise margin high is VOH minus VIH. Noise margin low is VIL minus VOL. Okay, those numbers you can get. 4.5 minus 3.2 comes out to be 1.3 volt. VIL minus VOL is 1.2 minus 0.9 is 0.3 volt. Okay. Then they're saying they're changing the logic levels for the input. So input 2 has, let me check it again. VIL is made 1.5 volt, VIH is made 3 volt. So this is VIH is 3 volt and VIL is made 1.5 volt. So this is the noise margin H2 and this is the noise margin L2. Okay, you can calculate. So which of these circuits do you think is better? Input 1 or input 2?
If the noise margin is lower,
Mm-hmm.
then the circuit is better.
Okay. Okay, since it's digital answers, I like a little bit of an answer, like a explanation. Why do you think so?
Because if the noise is been included in the input, then the output will be getting cluttered.
Okay, okay, so yeah. So actually, noise margin means it is a tolerance, it's a limit. It's like kind of like some, how do I say it? Like, suppose you, when you are designing some building or something, let us say building, you know that this beam can take weight of 10 kgs. Okay. But, but what, and your load is, let us say your load which is going to be applied for your building is 10 kgs. But your beam, you will not select a beam which can withstand 10 kgs. You will select a beam which can withstand 15 kgs or 20 kgs. You increase that amount. So if your noise margin is more, means your circuit can tolerate more noise. It can tolerate more noise. That is, its capacity to withstand noise is more. That is why when the noise margin is more, the circuit is better. Okay. Let me write. When noise margin is more, circuit is better. Okay. Anyone has doubts in this part?
No, sir.
Okay, fine. So now we have this question over here from CMOS. This is the question. Okay, it's looks very complicated and everything, but it's actually very simple. Also, I'll just share the link to the channel where I'll be uploading the video so you can see it. The drive link I have to create, but the YouTube channel remains the same. So let me just share it off with you guys. This is where I'll be uploading the video. So you can access that. So now, this is your circuit. So this is known as your pull-up network. And this is known as your pull-down network. So they have the opposite roles, right? If you want to find V output, you can either just look at the pull-up network or you can just look at the pull-down network. So if you look from the pull-out network, you will find it in terms of V output. If you analyze it from terms of the pull-down network, you will get it in terms of V output bar. Okay? Because both are doing the same thing. Like they're doing the opposite thing, sorry. Pull-up network will take it high, means pull-down network in that case, it will take it low. Or it's not exactly that case, they do complementary function. Okay? So if you either analyze the pull-up network or you analyze the pull-down network, you have got your answer. You have got your answer. So now, what do you see over here? You have A or B. This is actually your A or B. And then you have your C and D in series. And then this is your E. So your V output, you have what is known as your A or B, that is in series with C and D or E, right? Because this is like an OR function. If either A is, see, I'm making a mistake here. No, this performs the NOR gate function, so that's why there's a plus B OR. Okay, and this is again the NOR gate function. So, and as we know, like let us say this is like kind of a X bar and Y bar. This can be written as X plus Y bar, right? So it can be, see, it's making somewhat mistake. So, what is the answer given?
Sir, can I leave the meeting? So in my
Yeah.
hostel match was
Yeah, sure.
closed soon.
Yeah, sure. You can also go. Yeah.
Okay, sir. Thank you.
Thank you for staying so long. Yeah. So, A and B takes it low. C and D is like this. Okay, I'll get back to you guys regarding this one. We can either solve it in next class. I'm not exactly remembering how I solved it, but it's very simple. I think I checked it from the pull down network. I analyzed and I saw it. I'll have to check it. Okay. Achha. Any other doubts and queries of anything else taught? And can we end? And
Yes, sir.
okay. Okay, so I'll end the meeting. So this last part, there's some confusion. So hopefully next week we can look into it. All right. So thank you for joining. I'll be uploading this video soon. Okay.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Welcome. Thank you.